We're rolling. Welcome back. This will be video, what video is this? 6 or 7, right?
6.
We had like 5 videos for rotation. Oh, we had 5A and B, so we had 6 or 7 videos for rotation. This video is concentrating only on binding energy. Binding energy. Now, from the 10,000 foot view, what did we say about binding energy? 1 plus 1 does not equal 2. Does not equal 2. 1.1 plus 1 does not equal 2. If I have a gram of hydrogen and I fuse it with another gram of hydrogen, I am going to come up with something less than 2 grams of helium. Agreed? And that's fusion. That's what dominates our universe. All right? And where is that mass going into? It is going into the most important equation in all physics. It is going into E equals mc squared. There is a conversion between energy and mass. So that mass is going into energy. Agreed? And that mass is what? The mass of the hydrogen or the mass of the helium? It's the change. It's the delta M. It's the delta M. So the only thing you really have to concentrate on here, other than this E equals mc squared, is the conversions, because we don't like dealing with the 28 zeros of joules. We like to deal with electron volts, and we really like to deal with mega electron volts. And how many electron volts in a mega? A million. 1 times 10 to the 6. And I always forget it. What's the conversion between atomic units and kilograms?
1.6.
27 zeros, right? So that's the only killer in this stuff, other than this fact that 1 plus 1 does not equal 2. That some of that mass is 2. Let's do a quick problem. Let's say I have oxygen 18. Oxygen 18. That 18 corresponds to the atomic mass. It's a rough estimate of the atomic mass. For a more specific atomic mass, we should go to the periodic table, which is an average of all the isotopes of oxygen. Agreed? Okay, so 18 is a ballpark figure for atomic mass, but what it really is telling us is the number of protons and neutrons. And oxygen, anyone know we're in the atomic, with the periodic table?
7.
It's number 8, isn't it? It's number 8. Carbon, nitrogen, and oxygen. So oxygen is atomic number 8. Yeah. That means it has 8 protons. And this isotope of oxygen obviously has 10 neutrons. And if I tell you it has no charge, it's got 8 electrons. 99.9% of all the mass of this isotope of oxygen is located in the nucleus. The electrons are practically massless. Look at those numbers. And the electrons practically have no mass at all. So somebody crunch the numbers. We got 8 times, what's the? 1.00. 6, thank you.
No, 76.
Look at you guys. 1.0072, I guess like 76, thank you. And nitrogen 10 times 1.0086, 65. Someone do these numbers, please. And the electron 0.000 5486. Carry it out and get me a grand total, somebody.
18.149.
149. 2 more. 2. Those are atomic units. 18.14 atomic units. That is the mass of the components. Oxygen 18, more or less than 18.14. A little bit less. I'm making up a number now. All right, this is not, I don't know what the atomic mass of oxygen 18 is. You can Google it. I'm just going to make up a number, and that number is going to be 18.1481 atomic units. Okay? Don't hold me to that. All right? So now, some of the mass of the components went into energy and formed oxygen 18. So where am I going now? E equals
Oh, don't you have to convert those to kilograms?
Thank you, thank you, thank you. First we gotta find the delta M, and what's that gonna be?
That's subtracted by that.
Yes, I need a number, Murad.
0.00.
0.0011, Paul? Thank you.
Times.
Atomic units. Now I got to change that into kilograms because I'm using meters per second for the speed of light, and I'm going to have joules over there, so I need this in kilograms.
Right.
Somebody?
Multiply is 1.8.
1.8.
1.82 times 10 to the negative 30.
Times 10 to the negative 30 kilograms. All right? Somebody keep up with the calculations, please. I didn't do it. All right, so we got 1.8 times 10 to the minus 30 kilograms. I put this in here, and I'm going to get MC squared 1.82 times 10, negative 30, times C squared, C most important number in all physics, and that would be 3 times 10 to the 8 meters per second. How many miles per second is that? Inconceivably fast. 186,000 miles per second. Inconceivably fast. Someone, what kind of energy do I have here?
1.64 times 10 to the negative 13.
Negative 13, what are the units? If I have kilograms, meters, and seconds? Joules. Those are the units of MKS. 13 zeros, I don't want to deal with it. I'm going to convert that into electron. My favorite word, Kenny?
Photodisintegrate.
Photodisintegrate. It's almost as good as the space-time continuum, Tara. What photon is going to photodisintegrate oxygen 18? What does the photon look like? What?
More binding energy.
We're going to set up what equals this binding energy? E equals HF equals this binding energy. That would give me the frequency of that photon. Agreed? And how would I find the lambda of that photon?
E equals HC over lambda.
E equals HC over lambda. And HC is conveniently
1.99.
on your AP equation sheet, which everyone should have out in anticipation of our test in a couple minutes.
1.99 times 10 to the negative.
Thank you. An unsolicited answer. Those are the best kind. All right, can we do this?
Yeah.
All right, so once we get this binding energy, if we want to know the photon that's going to destroy that oxygen atom, HC over lambda. That would give you the lambda, or HF equals this binding energy. Are we in agreement? Questions? What's unclear? If you look at this video 6 months from now, you're going to walk into that test knowing this stuff, yes? Binding energy?
Yeah.
Mackenzie. It's this much energy. Let's use joules. It's this much energy, Mackenzie. So we need at least this much energy. That's the energy that's holding oxygen 18 together. So we need at least this much energy to blow it up. Does that make sense? We need at least that many joules to disintegrate it.
Mr. D.
So the question is, we're going to shoot a photon at it to blow it up. How much energy does that photon need? It needs that much energy. What's the wavelength and frequency of that photon? We would have to say E equals 1.6 times 10 to the minus 13 joules. That has to equal H frequency. That has to equal HC over lambda. This is the energy of one photon. So the energy of the photon that's going to blow this up has to have that many joules in it. So we're going to set that equal to HF. That's going to be the frequency of the photodisintegrating photon. And that will be the lambda.
Right.
Of the photodisintegrating. Does that make sense, Mackenzie?
Mr. D?
Yes, Steve.
The number that you have for electron volts is completely wrong.
Yeah, right.
Yeah.
This looks like a very little number, doesn't it?
It's supposed to be a big number.
Yeah.
6.25 times 10 to the negative times 10 to the 32.
Stephen, thank you. That did look like a crazy. What did we do? Divide? We should have multiplied.
I think.
What is it? What is it?
No, they multiplied. It's
What's the-
6.25 times 10 to the 32nd.
Thank you. 32?
Yeah.
Wait, are we dividing or multiplying?
Electron volts.
Divided.